Okay, so thank you, and yeah, best greetings from Mainz again. It has been a long day, so I hope yeah, I will be motivated in this talk and convince you a little bit more about modeling electrochemistry with non-equilibrium thermodynamics. So let's recap more or less the end of the story yesterday by showing you again from a rather mathematical point of view where we are, because the very question in the end yesterday, what about the dielectric constant, if this is not a constant, is exactly the next thing we're going to address. And in order to do so, just a little recap. So we consider a metal in contact with an electrolyte. In the electrolyte, we have solvent, anions, cations. On the metal surface, we have surface electrons, surface metal ions, and adsorbates in principle. And we consider diffusional equilibrium in both phases. So the gradient of the electrochemical potential is 0, or you can integrate this. We have electrical equilibrium, basically yielding the Poisson equation is equal to the charge density, the free charge density, which is built up of anions and cations in this case. And we have mechanical equilibrium, where the gradient of pressure balances the Lorentz force. Non-equilibrium, this would be the Navier-Stokes equations. And I tried to convince you yesterday that there are thermodynamic closure relations, or another wording for this is that you have chemical potential functions mu, which are expressed in terms of mole fractions y and the pressure p. And this V alpha term here encodes the partial molar volume here of solvated ions and solvent. And we have an incompressibility constraint. So this was more or less the setting we ended up yesterday, or all the images I showed you yesterday were more or less based on these type of models. And again, just because this becomes important over the next few slides, when you take this chemical potential function mu here, and you insert this in the diffusional equilibrium, you get this relation for the mole fraction, which has this tremendous difference to classical Poisson-Boltzmann expression. So the first part here is Poisson-Boltzmann, and the second part here, this pressure dependency, comes really from the incompressibility of the liquid, accounting for solvation effects. And due to incompressibility, you also have this denominator here in the charge density. However, you get in total a right-hand side, which depends on electrostatic potential and pressure. And you will see in a couple of minutes that when you make the dielectric constant, for instance, concentration dependent, then you will have here an even further complicated set of dependencies on other variables. So that's the reason why I'm doing here this recap. Yeah. So for incompressible solvation mixtures, we already get this coupled Poisson momentum equation system, where the charge density is a function of electrostatic potential and pressure. And you see in a couple of minutes how this changes when you make the dielectric constant not constant, but concentration and field dependent. So this is what we're going to discuss now in the next part. So this was exactly a question yesterday from the audience. What is happening when we want to change here that the dielectric constant is not a constant, but it is, for instance, concentration dependent, which is sometimes called dielectric decrement effect. So this is here for bulk effects, but it's pretty well known that when you put salt into water, the dielectric constant basically declines. And when this is happening in bulk, it also has an impact in space charge layers. And on the other hand, it's also, I mean, this was from Grahamy a statement, but there are strong indications that the dielectric constant is not really a constant, but also depends on the electric field strength. Yeah? And these two aspects are the ones which we are going to address now. So we want to have a dielectric now function which depends on anion and cation concentration, which depends on the electric field strength. Why there's a squared here incorporated, this is something I will tell you throughout the talk. And then in the third case, what happens when it's dependent on all of these three things. From a thermodynamic point of view, it's not really interesting to consider just the spatial dependency, because whenever we talk about fields, yeah, we want to ensure to have, I don't know, something like Lorentz invariance and stuff like this. So there's not really a spatial dependency, but it's always just dependent on thermodynamic quantities such as concentrations, electric fields. You can have, of course, also temperature dependency, but I'm sticking here to these three main aspects. The question is how to model this. Well, in the first place, you can just imagine that, well, isn't it just fine that we consider a dielectric function which depends now on concentration, electric field, and we plug this into the Poisson equation? Isn't this just meaningful or sufficient or however you would call it? And the answer is no, you can't. Because the whole equation system, which basically yields to the Poisson equation, has to be re-derived in this case where you want to employ such a kind of model where the dielectric now depends on concentration and field, because you will also have contributions of this to the chemical potential, as you will see in a second. I have a paper on this from 2022 in Electrochemical Actor, where the whole derivation of this is given, and I will sketch this now, how this is achieved. So basically, we always start from a free energy density of our mixture, and this guy now is also dependent on polarization, and you get a polarization vector. This is the partial derivative of free energy density with respect to P, and the chemical potential is the partial derivative of the very same free energy density with respect to mole fractions. And here you can already see when there's a feedback loop between polarization and concentration dependency, you will ultimately already get a dependency here in chemical potential. And another aspect, what is happening when you have this, is that you have something which is called penduromotive force. So you have on the right hand side of the Navier-Stokes equation not only electrostatic or Lorentz force, but also gradients of electric field times polarization vector. We also have a sequence of papers on the derivation of the field theory for this based on coupled electrodynamics and thermodynamics. So this is what is following now is basically a brief summary of these two papers. So what you do is you basically derive, let's say, the local second law of thermodynamics, where you account for the fact that polarization is a time-dependent quantity, and you can then really see that whenever the electric field is not equal to the equilibrium field, you will have an entropy production. This is basically written here. And this tells you how you have to choose the polarization vector with respect to E. And in essence, this is what we exploit now in the further. However, if you do so, you also have to take into account what is actually happening to pressure, because you have in electrodynamics, you also have something like the Maxwell stress, which is also affected by this polarization terms. And it's a little bit messy, but if you somehow believe me, this derivation, then the main point is really that you get something again like the Gibbs-Duhem equation, but it's a little bit more complex. So you're not having only gradient of pressure is here the molar volumes times gradient of chemical potentials, but you also have here again this penduromotive force term. In thermodynamic equilibrium, you still have again diffusional equilibrium, so this remains the same. You have a polarization equilibrium, you have mechanical equilibrium now with this additional term, and you and you have the Gibbs-Duhem equation, and basically this is, let's say, this shows you the consistency between, let's say, mechanical equilibrium and Gibbs-Duhem equation. This is somehow how thermodynamics and electrodynamics are tied together in order to ensure that something which is called total stress remains constant throughout the entire system. This is kind of like let's say the compatibility condition here. And now the main material model I want to show you in the following is a polarization model which is a function x, which depends on concentration and electric field squared. And for these polarization free energy, you directly get that the polarization vector is just chi times electric field. And you have a contribution to the chemical potential, which is just a partial derivative of this guy with respect to mole fraction, because that's simply the definition of chemical potential. You will also have something which is called polarization pressure. and mechanical equilibrium. And this is the explicit model we're going to use here, in this sense that the chi is basically scaling by 1 over the square root of electric field squared. This also has something to do with the idea that lower electrostatic fields are Lorentz invariant. So this is kind of, let's say, somehow the deeper origin of this. But just keep in mind here that the idea here is whenever you increase electric field, you decrease the dielectric constant. This is the idea why this is this shape. And why does it have here an E field square? Because, you know, when you're building here the partial derivative of this guy with respect to electric field, you have to get out a vector again. So from vector calculus, it's kind of, let's say, clear why you're having here really an E squared dependency. Okay, this is, it's a little bit of a tough syntax, but I'm trying to make this a little bit easier in the next few slides. So this is what we now have to solve together with the representation of charge density, diffusion, and equilibrium. And now you can already see what is happening. So if you compare this to the mole fraction we had before, so this here is the Poisson-Boltzmann or the Boltzmann expression here, the electrostatic potential dependency of Y. Here is the pressure dependency of Y. And now you're having this additional term here coming from polarization, or from, however you want to call it, concentration dependency of the free energy density contribution of polarization. So just to compare these two things, so with a constant susceptibility or dielectric constant, you have here on the right-hand side Poisson equation, momentum balance, and Q is dependent on phi and pressure. And when the dielectric constant is not constant but concentration and field dependent, you have a far more, let's say, a more complex coupling between pressure, electrostatic force, pendulomotoric force, and charge density, because this charge density Q is now a function of electrostatic potential, material pressure, and electric field compared to the ones here. In order to make this a little bit more systematic to be understandable, I will give you, let's say, 3 different cases. Case 0 is the one where we have a constant susceptibility, and case 1 is the case where the dielectric constant is electric field dependent. No, I'm sorry, I have here a twist. The case 1 is where we have a concentration dependency. So the first case, despite of having a constant dielectric susceptibility, is one where we have concentration dependency. So the dielectric susceptibility is the bulk one minus some contribution when you put salt in. Because we already know that from dielectric relaxation experiments that this is indeed the case. This is, of course, a bulk experiment, but when you are using now this model here, you exactly get this experimental result for bulk. And now we question ourselves, what is happening when we are using the very same model here in order to compute space charge layers and capacities and so on with the model I just showed you. Just as yesterday, however, now with this more sophisticated model for dielectric decrement. This is also working out when you have incomplete dissociation, as I have shown you yesterday, where we have a dissociation degree which is non-zero, but this is not the focus here. So we consider now that the dielectric constant decreases when you have a local increased concentration of either anions or cations. And case 0 is the one where chi is constant, and case 1 is one where the chi is self-consistently a function of anion and cation concentration. And this is what you get out of a PDE solution here. So since the local concentration of cation increases, here in blue, it's a little bit hard to see, but it's really increasing because it's forming a space charge layer. This equation tells you that necessarily the dielectric constant decreases here for a value. I don't know what value of d I actually have used, but this is just to show you a general the general trend that this is in principle working. And here is now a parameter study for different values of this let's say scaling parameter d here. So when you expectably, if you would increase the scaling parameter d, you can really see how the dielectric constant in space charge layers decreases from the bulk value 80 down to values of 50 or 40, dependent here on the solvation number. Here's for solvation number 20, and here is for solvation number 10. In accordance to that, I will show you now how the concentration here for anions in space is looking like. So here at x0 is always the metal surface, and you can really see that for increasing values of this dielectric decrement, you can see how the concentration necessarily has to decrease, again for large and smaller solvation number. So this is just the very first, let's say, systematic extension when you want to treat non-constant dielectric susceptibilities. It also does impact the differential capacity, as you would expect. Here again, a parameter study for various values of d, meaning that whenever you have a dielectric decrement, it's basically decreasing the differential capacity, which is also something you would somehow expect. And also already mentioned by people like Bockris in their treatise of electrochemistry, that they would expect that the dielectric constant in space charge layers is far larger than the bulk values. And this is exactly reflected here by this model. However, self-consistently in a thermodynamic consistent manner. Now, I don't know why I have here a twist, but this is actually, this should be exactly the other way around. So case 2 is, sorry for that, is where the polarization here is now, or the dielectric constant is now decreasing when the electric field is increasing. So the dielectric susceptibility here on the y-axis is decreasing when the electric field strength is increasing. And below here are again the numerical solutions of the underlying partial differential equations, where you can really see, okay, well, whenever I have a space charge layer, meaning that I have here an applied voltage of 1 volt between electrode surface and bulk, I can really see how the dielectric susceptibility decreases now because I have locally an electric field. Again, here for various parameters of this of A, which is here the main scaling parameter for the field strength dependency. Of course, this has a very strong impact, as you could expect, because if the dielectric increases from 80 to 0 in about, let's say here some nanometers, and I recognize Jörg's comment from yesterday, but I mean, this is field theory. We cannot just say here that this is not valid anymore. Nevertheless, this is what you directly would get as a conclusion. And in accordance to this, again, how the concentration of anions and here, for instance, of solvent also varies as a function of this scaling parameter A. This is, let's say, the second dependency of the dielectric decrement, here now the electric field dependency. Expectably, the impact on the differential capacity for this is pretty strong, yeah, because as I just mentioned, whenever A is getting pretty large, you will see that in some angstroms already the dielectric susceptibility gets away from the bulk value towards 0, and thus dramatically decreases the differential capacity. But from a framework kind of idea, it's just the natural conclusion you can draw. And of course, finding out now realistic values for A is of course one of the main let's say parts to be done here. And case 3 is now the combination of these two effects. So really we have a dielectric constant chi which depends on concentration and simultaneously on electric field. It's a little bit messy in order to show you how the whole equation system looks like. So maybe I try to be a little bit more precise here for this very specific case. So now we have a dielectric constant, which has, first of all, it has a bulk value, and the bulk value is decreased when you have a local increase of salt concentration, and simultaneously the dielectric susceptibility decreases when the electric field strength increases. And by this, you have a contribution to the chemical potential, which is basically this here. So the chemical potential is now dependent on the square root of electric field strength. And in diffusional equilibrium, this really means that the mole fraction now depends on electrostatic potential, on pressure, and also on the gradient of phi, which is something totally different than we had before in the case where you only had constant dielectric constant. So this is really superior. And in that sense, the charge density, because if you insert these guys here for y, becomes phi, pressure, and field dependent. And also you have to plug in this here again back up here in order to get the susceptibility as a function of pressure, electrostatic potential, and gradient of phi. This looks messy, but still it's solvable, and it also, we can prove that this is remains elliptic. Yeah, so this coupled equation system now is really, let's say, the straightforward extension which thermodynamically consistently is obtained when you have a dielectric which depends on concentration and electric field. And that this is that this guy here remains elliptic seems surprisingly in the first place, but it's more or less relying on the fact that that you have always here electric field square terms and not just electric field terms. So this equation system, which is written down here now, it's looking a little bit messy, but you can solve it numerically. And here is what you get. So on the left side, again, dielectric susceptibility as a function of space for different parameters A, and on the right-hand side, the electrostatic potential. And the accordance that the Poisson momentum equation remains elliptic is somehow coincides with the fact that phi remains monotonic. So if phi would become non-monotonic, then this could also change here the ellipticity or the solvability of the underlying Poisson equation. Surprisingly, what you now can find is oscillations in space for the anion or the solvent concentrations in space, just because it's now a balance of the electric field strength between attracting anions, and then somehow it's becoming more favorable to agglomerate against solvent, dependent here on this parameter A. But in principle, this should just show you that even though that from a continuum thermodynamic point of view, you can still get this kind of, let's say, oscillations, however, just naturally by the self-consistent incorporation of concentration and field dependency. Here's now an overview of this 4 different models for chi and how they impact the dielectric or the differential capacity. So red is for a constant value of chi. Yellow is where it is field dependent. Magenta is concentration dependent, and blue is concentration and field dependent. And as you would expect, the field dependency really dramatically kicks in the sense that it's decreasing capacity values beyond minus and plus voltage values beyond the maxima terms. So in that sense, I believe that from let's say a broad data set of capacity measurements, you can basically reconstruct really whether the electric field dependency of chi is as strong as Graham suggested or not. I don't believe that it is so strong. There could be some, but not so strong as for instance showing here. So I believe that the dielectric constant maybe goes down to values of, let's say, 30 or 40 here for this dash for dark blue, but getting really to 0 is, in my opinion, not too realistic when we compare this to experimental data. So this as a recap, in order to just give you a feeling of what you can all do in this framework. Also, when you consider here dielectric constants, which are now concentration and field dependent, and this slide here should again tell you that everything I just told you until now was in equilibrium, and now we wanna. I mean, we also want to study, of course, systems where we are in non-equilibrium, and you can already see in the first glance that this is becoming messy. However, we already know or learned a lot of things by the previous studies. For instance, we now know how the chemical potential functions look like, and this is what we are going to discuss now in the next couple of minutes. Yeah? So the transitioning now from what we have learned from equilibrium situations in terms of chemical potential functions, transitioning this to non-equilibrium cases. When you step back and ask, and I guess Jürgen also told you about this, so classical Nernst-Planck flux, for instance, you find that ion fluxes is proportional to gradients of chemical potentials, or even here combinations of chemical potentials of solvent and of anions and solvent. And when you try to plug this into a relation which looks like a diffusion equation, you always get this guy which Newman and other people tend to call thermodynamic factor. This is basically the partial derivative of the chemical potential here with respect to concentration. You're doing this in order to obtain here a gradient of concentration. And the funny thing is now that this guy here, yeah, which if you look into this equation, this gives you a lot of the, let's say, concentration dependency of a diffusion coefficient, or the chemical part of this. This is something you get for free when you know what the chemical potential function is. And I hopefully convinced you somehow that you can validate this chemical potential functions by capacity measurements. And based on this, you can predict basically what the thermodynamic factor is. And by accident, I found out that people here from Munich University, so Hubert Gasteigger, they really can measure this thermodynamic factor, and we are in quite well agreement. So this thermodynamic factor is really a prediction based on this solvation mixture model, and this is what they measured independently from diffusion experiments. So this is also a nice hint showing what you can actually learn from capacity measurements, that once you have determined mu, you already know a lot of things in terms of concentration dependencies of the non-equilibrium part, yeah, in sense of concentration-dependent diffusion coefficients. Another aspect I want to point out here for electrolyte transport is cross-diffusion coefficient. So classical Nernst-Planck type fluxes assume that the flux of anions is proportional to the gradient of the electrochemical potential of the anion, and for the cation, of course, of the cation. If you rewrite this here in a more or less well-known relation, where you can state that the charge flux of cations is a diffusional term with respect to electric current. Here's transference number. Why is this meaningful? Because you can experimentally access here the molar conductivity in a manner that when you can build a situation where you have no concentration gradients, you can really measure the molar conductivity. And this is nice because the molar conductivity is the only non-equilibrium parameter which arises without having gamma terms involved. Yeah? So every other non-equilibrium parameter in diffusion relations always involves somehow the gradient or parts of the chemical potential. However, molar conductivity is the only one which does not have this contribution. And this is nice, and was also known in electrochemistry quite well. And already in the 1919 around, Kohlrausch found out that the molar conductivity basically depends also on concentration. And Nernst-Planck states that this is a constant. So this is kind of, let's say, contradictory. People ignore this throughout the literature because they say, well, this effect is not too large, but it's just, again, a way of how to look onto this. You can simply account for this when you consider cross-diffusion terms. So the entropy production due to fluxes allows you that you're not having, that the flux of anions is not only determined by the gradient of the electrochemical potential of anions, but also of cations, with here a cross-diffusional term, and vice versa. The flux of cations also has contributions of the electrochemical potential of anions. And then you have an additional quantity, which is sometimes called friction term between anions, cations. And this friction term fascinatingly actually propagates exactly onto the point where you're getting here then a minus term of arising from this friction term. And this basically reproduces Kohlrausch's law from the 90s. Yeah? So in that sense, you can somehow more or less simply explain Kohlrausch's law by the idea of cross-diffusional terms in Nernst-Planck type fluxes. Now, if you remember, our chemical potential functions, they were, even though the ones with constant dielectric susceptibilities were a bit of a mess. So you had concentrations of anions themselves, of solvent, of pressure. And when you plug these in, you have this mess of, let's say, gradient terms. So the flux of anions here has now a contribution of concentration gradient of anions, concentration gradient of cations, of solvent, of pressure, and of electric field. But that's just how it is. And a lot of, let's say, ambiguity in experimental data comes from the fact that people try to, let's say, condense all of this into a simple diffusion equation, a linear diffusion equation, which is just not there. And whenever you have electrolytes, you have all of these effects here, which you can get, because if you're using this flux relation here and set up by boundary conditions an experiment which corresponds to the ones for an electrode charging, you get back the differential capacity curve. So this flux here automatically predicts exactly the capacity curves which we were discussing now for 1.5 days. Yeah. So as mathematicians, I mean, this is of course nice because it gives new math and so on, but people always try to make things easier, and the mathematical sound way to make things easier is, for instance, asymptotic expansions. Because whenever you want to study, let's say, more macroscopic systems like batteries or fuel cells or whatever, you not always want to resolve spatially the whole space charge layer or double layer, and you can do this by what people call matched asymptotic expansion. So just by figuring out that this, the spatial dimension of the space charge layer L3 is compared to, let's say, a macroscopic electrolyte rather small, you can do mathematical tricks in order to shift this space charge layer into effective new boundary conditions, which gives you then, for instance, the potential drop across the space charge layer, diffusional equilibrium within this new interface, strong electron neutrality outside of the space charge layer, and new boundary conditions which capture surface reactions. This is here, this guy, and also variations of the space charge layer, which is this guy. This can be done mathematically sound and rather general way. So this is basically these two papers here. And what you then get is, for instance, that you have a boundary condition here at an interface where the space charge layer was asymptotically condensed into a new singular surface. You get Neumann boundary conditions which account for capacitive terms and surface reaction terms in terms of, for instance, when you have a redox shuttle, for instance, then this could be one part of the reaction, or another branch of my research is lithium batteries. So this R can also be a lithium intercalation reaction, which I want to tell you something about in the next couple of minutes. Just let me point out here, this guy here, so this boundary condition basically came from the general case of, I don't know why here an S is, so this is typo, but this boundary condition has, let's say, its superior version, which is the balance equation for some species which live on the surface. So a concentration on the surface can change because something is flowing through the surface and something sticks onto the surface, because the surface can grow in size, or because something is reacting on the surface. And when you assume that something is not agglomerating on the surface and that the curvature doesn't play a role, then you get back to what I've stated here. So just to let you know that all of what I told you right now is also working, for instance, for bubbles which are forming, or for nanoparticles which can grow. If you now exchange the electrode from a metal towards an intercalation electrode, then also from a mathematical point of view, a very interesting reaction you can study is the intercalation reaction, here written for lithium. So we have lithium and an electrolyte, and this is at such an interface forming an intercalated lithium ion. And because lithium ion was solvated, it strips off its solvation shell, so it's freeing up copper solvent molecules. And one, let's say, delicate question is how to consistently model this, also with respect to what we have learned over the last 1.5 days. And again, here, when you strictly stick to this framework of non-equilibrium thermodynamics, here surface thermodynamics, then you get automatically how the dependency of surface reaction rate depends on quantities evaluated directly here at the interface. So the surface affinity, the driving force for the surface reaction here is really, let's say, this linear combination of surface chemical potentials. And now we can draw them back through the space charge layer. So the lithium reaction here at the interface, you pull them back through the space charge layer. That's the reason why you see here this guy. That's the chemical potential of cations outside of the space charge layer. However, if you do so, you get additionally the contribution of the electrostatic potential drop through the space charge layer. And this representation here ensures something which is called the second law of surface thermodynamics, so that this always is non-negative. Why is this important? Because through our battery literature, this is not always the case, unfortunately. And I will try to give you a short feeling of where this is, where there can be discrepancies. So for a closed system, and I'm not going to talk a lot about intercalation electrodes here, but you will need also material models for intercalated lithium here on the electrode side in order to close the system. What is important, just to mention here, with this respect, is once you have, I mean, we were talking a lot about the electrolyte. So we have in the electrolyte, we already know chemical potential functions here for lithium, and we already know how electrostatic potential and also pressure comes into play. And the same in principle holds also true for the active phase. You also have a chemical potential of lithium, and you have an electrostatic potential in the active phase, coming from electron transport. And what is of ultimate importance for consistency is that you are using really the very same chemical potential functions which you are using here in the transport equations, also in boundary conditions. And so exactly the mu's which you are using here in fluxes are also employed here in boundary conditions. And the same also holds true for the electrostatic potentials. And this is something which is not, let's say, very precisely be always done throughout literature, at least what I found out by studying this. But when you ensure this, you ensure overall thermodynamic consistency between the, let's say, two phases and their common interface. And this is, of course, well, not only in my opinion, but from a consistency point of view, necessary in order to have really predictive value, which is what we want to have in the end for these type of models. Just to give you a feeling what you can do with this now, a very nice, so the equivalent of let's say a single crystal electrode in contact with some electrolyte on a battery level is a thin film, a dense, non-porous, dense, thin film cell, for instance, sputtered on a single crystal electrode in contact to some electrolyte. And when you do this, you can directly measure the cell voltage as a function of status of charge, and simultaneously with respect to the current density with which you discharge the cell, sometimes also called C rate. And this is somehow the analogy of differential capacity curves for intercalation electrodes. Here is a data set, for instance, for this thin film cells, where you have a variation of C rates. Of course, be careful, this is really thin film, so you can have very high C rates. And this is what you can get by, let's say, the modeling procedure I just showed you. Again, this is, let's say, a validation methodology, if you want, for also intercalation electrode and surface reaction models. Why is this important? Because we now can propagate, again, mathematically sound, we can propagate everything we learned on the thin film cells also towards porous electrodes in terms of mathematical homogenization. So you can have a porous medium where we can basically all we have learned now use in terms of multi-scale asymptotic expansions to derive PDEs for homogenized porous electrodes. Maybe this is a little bit too much, but for people for battery research, this is something which in the end looks a little bit like a Newman type model, where this guy here is the diffusional corrector, or sometimes called tortuosity, for a specific microgeometry. This can also be done and has been done at our institute also for more complex geometries like real porous electrodes. So this is a reconstruction of a PIP-SEM image of a porous electrode, and you can really compute then, for instance, how the effective diffusion coefficient in all three main directions looks like. So that's here the story. All of which I have told you before in terms of continuum modeling of electrolytes and interfaces can directly be employed towards homogenization theory in order to have PDE-based models, for instance here for porous battery electrodes, which again, if you build up a system, if you plug in the boundary conditions for differential capacitance, you get back these capacity curves, which is, in my opinion, pretty nice. For porous electrodes, then you can already see that the C rate really gets far smaller compared to thin film cells. This is again just for validation steps. This also works for many particles which are non-spherical, but this is just an outlook. And here, this is something really I'm working on right now, that this is also working for hysteretic materials where you have phase separation among particles. Again, everything with in let's say built up on the same framework of non-equilibrium thermodynamics. Here it's pretty nice. Skip here a little bit forward, because we can also compute sub loops where you switch from charging to discharging on one of these arcs and see what is happening here and how you get back from one plateau to the next. But this is something when this is of interest, we can talk about this more when I'm in LA. An outlook of what, in my opinion, can be done in the near future, but this is to consider more surface reactions, and in terms of batteries also, for instance, metal air, metal sulfur, or a general electrolysis. So one of my key, let's say, driving motivations for this is to somehow reproduce in the CV of platinum, which is yet outstanding, and I believe that this is possible. So this is where we are already there. So that's kind of, let's say, CV simulations I can do for water splitting. Of course, whenever you have more surface reactions involved, for instance, here forming surface, really new surface species, then as again, there was a comment yesterday, questions how this affects the work function and so on has to be incorporated. In principle, this can be done. That's also the reason why I'm doing this in a framework-like manner. And this is ongoing work. Maybe one more thing here to give you a feeling of what this means. So I already told you that we can have adsorption of some surface species here. But what is yet open is when you have a surface species which can really on the surface and adsorb it, forming with a metal ion on the surface a new surface species like adsorbed H or surface oxides and so on. And for instance, here this is well known for gold that this is happening. And from a mathematical point of view, this has to be done in terms of surface phase fields, where you can have really on the surface, then in tangential directions, the formation of islands, which then have their own evolution equation in terms of surface phase fields. So this is an outlook, and I'm happy, and hopefully we can discuss this in LA. And this is it for today.